Hi folks, we're going to take a look at page 344, number 10 from the Unit 5 assignment. So here, they want us to find an equation that describes all the points which are equidistant, so meaning have the same distance to both point A and point B. Okay, so let me represent this with a diagram here. So say I've got A and I've got B. So I'm looking for some point, okay, or to represent some point which has the same distance to both A and B. Okay, now when I'm drawing these diagrams, I always try to not pick the most obvious point. So obviously the midpoint between those two is going to be the same distance. So let me pick some other point as a representative. So I need this distance and that distance to be the same. I don't know what this point is, and there's many of these points that I can draw. So I'll call it P, and I'll label it as having coordinates x, y, z. Okay, now these distances are equal. So in what way can we represent the distance between 2 points? Well, what we can do is we can create the vectors joining the 2 points. Okay, so the vector from A to P and B to P. Okay, and we know that the magnitude of this vector will just represent the distance between the 2 points. Okay, so this is how I'm trying to apply the tools I have at my disposal to solve this problem. Okay, so this means that the magnitude of AP, okay, is going to be equal to the, or needs to be equal to the magnitude of BP. Okay, so this is where the vectors part of this problem comes into play. Okay, is recognizing that I can find such a point which is equidistant to both A and B by using the magnitude of the vector formed when I join these points. Okay, so now let me apply my my formula. So AP is found by subtracting the second from the first. Now notice here, it's not by accident I chose to do AP and not PA, because I'd like my variables to come first. Okay, so I'll skip the step of actually writing out the vector AP, because I think we can do it. So the x component, let's remember that the magnitude of vector is the x component squared plus the y component squared plus the z component squared. So the x component of this vector here would just be x minus 2, the x component of A, so that's x minus 2 squared, plus the y component squared, so that'll be y minus negative 1, so y plus 1 squared, plus z minus 3 squared. Okay, and that needs to be equal to the magnitude of the vector BP. Okay, so the coordinates for BP will be the x coordinate, x minus 1, so I'm going to square that. Okay, y minus 2, we'll square that. And then z minus negative 3, so that'll be plus z plus 3 squared. Okay, so this now is the equation that I can use to try to come up with my answer. Okay, so at this point here, the rest of this is just going to be algebra. Okay, so I've got a square on both sides, so we'll square both sides to get rid of the square root. Okay, so square roots are going to be gone on both sides, and while I'm at it, let me expand these binomials. So x minus 2 squared is going to be x squared minus 4x plus 4. Okay, plus this binomial squared is going to be y squared plus 2y plus 1, plus that binomial squared, z squared minus 6z plus 9. Okay, and I'll do the same thing on the other side. I'll just expand these binomials. So I've got x squared minus 2x plus 1 plus y squared minus 4y plus 4, and plus z squared plus 6z plus 9. Okay, and as we've seen this type of problem before, we see that the x squareds on either side cancel out, and so do the y squareds, and so do the z squareds. Okay, and in fact I see something very nice, because I have a plus 4 and a plus 4. So subtract that out from both sides. I've got a plus 1 and a plus 1. Subtract that out from both sides. Okay, I've got a plus 9 and a plus 9. Subtract that out from both sides. So what we're left with now are just x, y, and z terms. So here we've got negative 4x, and there we've got a minus 2x, so bring that to the other side. So negative 4 plus 2 is negative 2x. We've got 2y plus 4y, so plus 6y. Then here we have negative 6z minus another 6z, so minus 12z, and I've just got equals 0. Okay, and just for good measure, a nicer way to write this equation, I'll divide both sides by -2 to simplify it a little. So then I'm just left with x minus 3y plus 6z equals 0. And that's as far as I can simplify it. Now, I shouldn't be surprised that I don't have one specific answer here, because just looking at this diagram, well, there's lots of points. In fact, any point on this line will be equidistant, will be equidistant to both A and B. And in fact, since this is in 3D, hey, this point here is also equidistant to A and B. And I've got a point up there, which is equidistant to point A and B, if you can sort of picture that. Okay, so not surprisingly, I have something that still has variables in it. So that's my answer for A. Now my answer for B asks me for 2 such points. Okay, well here now, all I have to do is find x, y, and z values that satisfy this equation. Now I would say there's a really obvious one. Since I have these 3 terms equal 0, well, if each one of them is equal to 0, well, 0 minus 3 times 0 plus 6 times 0 is going to be equal to 0. So there's no real work to do there. I think that one's we can see pretty clearly. The question is how do I find other points? Well, if this were just x minus 3y, and we wanted to find different ordered pairs that satisfied this equation, what would you do? Well, you'd say you'd pick a value for y and then solve for x. Here, we'll have to pick a value for both y and z and then solve for x. Or you could pick a value of x and z and solve for y, or pick a value of x and y, solve for z. So that's how you can generate other points or other coordinates for our points P. Okay, so what I'll do here is I'll say let y equals 1 and z equals 1, make it nice and easy. And so x is just going to be x minus 3 times 1 plus 6 times 1 equals 0. So x is going to be equal to, well, negative 3 plus 6 is 3. Bring that to the other side, negative 3. So another point would be negative 3, 1, 1. And I can find infinitely many points by just choosing values for 2 of the variables and then solving for the third. Okay, that's it for this one.